We are starting right now our last session in our conference, and this is going to be shorter than the previous ones. This is the session that is going to be regarding the multidimensional cyber defense. And although we were published in the agenda that there will be 3 speakers in this session, there are going to be 2 very interesting speakers that will touch 2 different sides of the more holistic part of cyber defense. We enjoyed this morning along the day to hear several different sessions. Each one of them was very focused on one discipline and covered different types of achievements in this discipline. And this session is going to be more holistic, trying to take a kind of a challenge of the cyber defense and implement it in one of the disciplines. We are going to have, as I said, 2 speakers, and we will start immediately with this session. So our first speaker came just recently from Singapore to join this conference, and I have the honor to introduce Professor Abhik Roychoudhury. He is the professor of computer science at the National University of Singapore, NUS, in which we are these days building the relations of this university with the Tel Aviv University, and he is the director of the National Satellite of Excellence in the Center of the Satellite of Excellence in the Trustworthy software systems at Singapore. He is currently leading the Tsunami Research Center. This is a large research center funded by the National Research Foundation in the domain of trustworthy software as well. He is also the lead principal investigator of the Singapore Cybersecurity Consortium, and he is involved in several other initiatives and research centers, as well as a very known scholar that has published in a very leading papers and presented in nice, important stages. So this is my honor to invite you to the stage, Professor Roychoudhury. Please.
Yeah. A little different arrangement. Oh, okay. Reversed, yeah. Okay, thank you for the invitation, and it's great to be here. I will talk about trustworthy software, which is what I research in. So we have discussed quite a bit on the implications if the software is not trustworthy, implications in terms of policy, law, as well as the previous session was on cryptography. So my research is more in the technologies for making software more trustworthy. specifically as Dr. Harrell mentioned, I'm primarily working in program analysis and software security. And recently we have launched a number of initiatives to build up a holistic ecosystem in this and other related areas, including the Cybersecurity Consortium and the Satellite of Excellence in Trustworthy Software Systems. So the viewpoint that I will take, this is a beautiful picture of the Himalayas. So the viewpoint that I will take is not only the conceptual viewpoint that software should be trustworthy, what would be the implications if it is not, but also a little bit of the technical viewpoint. That means what are the technologies through which we can make software a little bit more trustworthy, how we can go towards something like a certification. So, and the kind of technology that I'm using quite a bit is the symbolic program analysis, but it's not a panacea. It cannot be used in all settings, so we are really combining it with other kinds of techniques like search techniques. So, just going into a little bit into the details of the kind of problems that one looks in the domain of trustworthy software. These are the kind of problems. The first one probably being the most closest to the industry. If you are really interested in finding out vulnerabilities in your programs, you will probably be using something like fuzz testing. Fuzz testing is a very well-known technology where you essentially feed semi-random inputs. It's not a random search, but a biased random search. You feed semi-random inputs and you are trying to find out crashes and hangs in your software. But there are also other kinds of problems like continuous fuzzing, crash reproduction, reachability analysis, localizing, and the one that I will talk about, that is patching. So oftentimes when we talk of trustworthy software, we might think of it in a very specific way, like just finding bugs, but the general area is bigger. But still, we can, in terms of techniques, we can look into two specific classes. One is the random search or the biased random search. These are a little bit less systematic. They are more commonly used in the industry. They are easy to set up and they execute up to a time budget. And the other class of techniques, which is the symbolic execution, they are more systematic, they have more involved setup, involve some backend solver calls. So of course, there is always a question about whether you want to go through this effort. And I'll try to give two examples, the first one more briefly and the other one in a more involved way, where we can see that which one fits depends on the problem in question. So this is the first example, which I will mention briefly. This is really the picture that you see on the left-hand side. This is really the state-of-the-art technique that is used today for the purpose of finding vulnerabilities in your software. This is something that scales very well. It scales to the extent of finding vulnerabilities in your Acrobat PDF reader or media player or something of that sort. Okay? So the technique is really very simple. You start with some sort of a test suite. So if you are interested in finding vulnerabilities in the PDF reader, you would typically have a good set of PDF files that is expected. And you go through a set of mutators. So the mutators will try to mutate the good PDF files to produce some slightly invalid PDF files, if it may. And then you try to guess or estimate which of them are considered as interesting inputs. So this estimation is based on some compile time instrumentation, and based on that you will probably retain some of these inputs and submit them for further examination. So further examination means that you would actually mutate them again and again and again. So this flow, so to say, essentially this iterative flow, it does not consider in any way which of the paths of the program are likely to be gone through or traversed through many inputs. These are typically the paths where you are probably doing some very simple checks and you exit out of the program very quickly, and which of the parts of the program would be traversed by very few inputs. And this is really where typically the vulnerabilities are. Because if you exit out of the program very quickly, it's unlikely that there is a vulnerability in that path. But deeper down, where the path is looking at valid inputs, but probably there is a vulnerability which can be exploited. So this is something we looked into. We tried to make this random search a little bit less random. That means how many mutations we will generate out of this test suite, out of these so-called good PDF files, if you're fuzzing the PDF reader. How many mutations we will generate, this is something we make decide based on whether it is going through a shorter path or a more or a less popular path, whether it is going through a more popular path or a less popular path. So when you think of it in hindsight, this is indeed what should be done in any semi-random search technique like this. That means the paths which are very highly probable, which are traversed by many tests, those should be given less probability in the testing because they are likely being traversed anyway. And the paths which are probably very less probable, that means there are very few inputs which go through it, those are the ones which you should try to preserve. So this is the technology that we have built. This is one sample capability that we have built, in fact, in Singapore, and which subsequently we have also transported to the AFL fuzzer, which is the one that is given out from Google Brain, and this is the one which is actually used. There are only two fuzzers currently, the AFL fuzzer and the lib fuzzer, which are used for the purpose of finding vulnerabilities on a regular basis for the purpose of corporations. And we are trying to work with both of these teams to incorporate this technology. So this is an example of how you can probably make the random search less random. But the random search doesn't always work. And this is another example, the one which we will spend more time on, that I'll spend more time on, which is the task of repairing a program, not just finding the vulnerability, but also repairing it automatically. This is something a lot of people tell me, well, this sounds like well, a little bit like science fiction maybe, but it's not really so, because there are certain common patterns that you can exploit. Those are easy to see, but my task here is to develop, as far as possible, a fully general program repair system. The inputs and outputs are very clear. There is a buggy program or a vulnerable program, and there is a correctness criteria. The correctness criteria is typically given in the form of test cases, because we don't want the correctness criteria to be in the form of formal specifications or assertions and so on. And we want to generate a patched program. So the application of this is very many. So there is application, for example, in the military for the purpose of building self-healing systems in the drones. You could try to patch security vulnerabilities. There is an application in post-secondary education, for example, for the purpose of grading student assignments and also for maintaining legacy software. So this problem, if you think about it, there is also, given a buggy or a vulnerable program, there is a search space of edits. So this problem can also be seen as a search problem, except that the search will not work very well because the search space of edits is huge and you may not have a very good way of guiding the search. So in this case, say the input is really, say, this buggy C program, and you try to generate mutations of it and evaluate the fitness. The fitness would be the number of tests that it passes among the test suite that you have. And if you have found one that passes all the tests, then you are happy. So my goal here is to replace this flow, because this would not work very well for the purpose of automatically repairing the program, because it would tend to overfit the test data. And this kind of a search, even if it is intelligent, it will lack imagination. So what we would like to do is to have this buggy program and tests, but from the tests, try to generate some sort of specifications. So note that these are not formal specifications that I expect anybody to write for me, but I try to generalize the tests into some sort of poor man's formal specifications, which I will use for the purpose of program repair. So I'll illustrate this. I'll not, of course, get into the technique, but illustrate this through this very simple example, which all of us would know, because all of us have gone through middle school and high school. So this is just the triangle example, which takes in three sides, A, B, and C. So it tries to decide whether this is an invalid triangle, equilateral triangle, isosceles triangle, and scalene triangle. There are actually several bugs in this program if you study this carefully. But the one that in this case I'm trying to patch, and the one that is demonstrated by these test cases, is the definition of this isosceles triangle. So as we know, triangle is isosceles if two of the three sides are equal. So this should be either A equal to B, or B equal to C, or C equal to A. Okay? So if you just try to generate more and more edits of the program, even if you have a very intelligent search, that means you generate the entire search space of edits that you can by copying the code elsewhere from the program, and then you try to traverse this search space. As it turns out, by traversing all the mutations of this particular line, even if like somebody comes, an angel comes in our dreams and says that, okay, this line is important, and you try to generate mutations of this line, it turns out that the search technique will not work. And the reason for this is very simple. The reason for this is usually the search techniques, they're trying to copy a correct code from somewhere else in the program. So it's a little bit like, suppose you try to go to play football and you lose a little bit of skin in your feet while trying to maybe dribble, and you try to maybe copy some skin from your hand and put it in your feet and try to see if it works. So this is what the search techniques would try to do. And in this case, the correct fix is such, even in this very simple example, the correct fix is such that the A equal to C, this never appears anywhere else in the program. So you would not be able to, however intelligent the search may be, however much guidance you may provide, you would not be able to generate even this very simple fix. So what would the semantic technique do? I would not get into the details of it. It would just try to convert this task of generating the fix as one of synthesizing a mathematical function. So if through fault localization I know, so of course that's a big if, that's a separate step of localizing where to do the fix. If I know that this is the line that I have to change, then I say that, okay, instead of this A equal to B or B not equal to C, I have an unknown function of A, B, and C, because these are the live variables in the program. I have an unknown function in terms of A, B, and C, and then I'll try to synthesize some small properties about this function. So for example, from this, some of the tests don't even reach this particular location, but from 4 of the 6 tests, I actually get a property of this unknown function that for 2, 2, and 3, it should return true, 2, 3, and 2, it should return true, 3, 2, and 2, it should return true, and 2, 3, and 4, it should return false. So this is exactly the definition of the isosceles triangle that it tried to synthesize, that it ended up synthesizing from the test cases and generalizing it. And if this is given to any modern day synthesis engine, program synthesis engine, it would be able to generate the fix. So another way, just a schematic way of comparing this, the syntax-based approach versus the semantics-based approach, is that the search-based approach would try to search among the set of edits and try to check against the correctness criteria, which is the test cases. Whereas instead of trying to search, you can ask yourself the question, what is the minimal change in the program that would make it right? Okay. What is the minimal change that would make it right and make it pass the correctness criteria, and then try to synthesize one such fix. So this is really what the semantic approach is trying to do. I'll probably skip this one. This has quite a lot of the symbolic formula. So this is exactly, the symbolic execution is the technology through which we are extracting the specifications from the test cases. So we do a concrete execution up to the line where we want to fix, and then do symbolic execution to extract the specifications. And this is the overall workflow that we end up with, that we have the initial set of tests with the oracles that are given to us. Then we do fault localization, which is a statistical technique, which points us to possible places where we could fix. Of course, this is possible. So again, we can try in multiple locations. And then through the symbolic execution, we try to generate a constraint that the program should satisfy, and then the synthesis gives a patch which satisfies the constraint. So we have investigated various modifications of this workflow to improve the scalability versus the overfitting versus the applicability. So of course, in the end, we want a program repair engine which is first of all applicable to a wide variety of programs, in general to a programming language like C. It suffers from very little overfitting. That means it's not restricted to the test cases. Because if you have overfitting, given any tests, you always have a certain patch. You can return if input 1, return output 1, if input 2, return output 2, and so on. That's not the repair we want. And also it should be scalable. So we have experimented with a lot of these workflows, including generating concise semantic signatures from the symbolic execution. And here is, just to show the scalability of this, this is really the kind of programs for which we have produced a lot of these repairs, including Wireshark and so on. And here, for the purpose of interest, actually I'm showing you the fix generated for the Heartbleed vulnerability, which some of us may be familiar with. So this is really the buggy part of the Heartbleed vulnerable OpenSSL. And this is the fix that is generated automatically. You can compare it with the fix that the developer had provided, which is not identical but functionally equivalent. So in this case, the fix generated automatically, this was actually the missing check on the payload. So of course this is anecdotal evidence. I can only give interesting examples like this. But we are currently trying to work with the fuzzing engines that are actually given out by Google to produce this fix as a backend to the fuzzing. That means as the fuzzing is done, the fix would also be done as part of it, and I'll try to explain how that is done. So this is actually the flow. I come back towards the end. I come back to this particular flow that we had seen earlier. This is the flow for fuzzing. That is, given the test suite, you mutate, generate the mutated files, retain the interesting files, and submit them for further examination. So the way we have we are trying to link up the patching so that the fuzzing and the patching, these are done really in one iteration. Because currently the problem in software vulnerability is that even after lots of vulnerabilities are detected, they remain unpatched for very long. So that's why we want to have the fuzzing and the patching as one iteration. So we will retain a symbolic representation, not a concrete one, but a symbolic representation of the pool of patches. And then we will use this flow, the fuzzing flow, to generate more and more test cases. That way you risk less overfitting because your test suite becomes larger. We generate more and more test cases, and based on this we refine the pool of patches, and we can automatically rule out a lot of the patch candidates. Of course, this would work only for certain kinds of errors. This would not be a fully applicable program repair system for any bug. This would be only against vulnerabilities which are observable through crashes. So those are the ones that we are trying to fix. And just to put the big picture, since Dr. Harel mentioned this, so and I am also here, I thought I should mention a little bit about where some of this research is being done. Some of this research actually is being done, and since the practical application of this is quite large, is being done in the context of the Singapore Cybersecurity Consortium. It's really a consortium. It's the first consortium in computer science. We used to have consortium in natural sciences like physics, but this is the first one we set up in computer science. It's a consortium of about 50 companies, the academia, government agencies, and also the National Research Foundation. So again, we have companies which are in different stages of evolution. We cannot expect all of them to engage with us in research, specifically in fuzzing research. So for some of them, we conduct training. We engage with them via training. So in fact, we organize an annual or twice in a year cybersecurity camp, as well as a lean launchpad for the aspiring startups. We also have technology talks while in Crazy Ideas Day and special interest groups. And finally, we actually have joint R&D funding, which is not given to a company and not given to academia. So I know that the Blavatnik Center also gives out research grants. So this is given to a company-academia pair. And whatever research is built, there is an infrastructure sharing with the rest of the members of the consortium. So this is maybe a little bit about the larger ecosystem. We started with about 14 members. Currently, there are 47 member companies. But to have targeted discussions, we have special interest groups because all the 47 members may not be interested in software security. So that is one of the special interest groups. And just to put an even bigger picture, this is the overall capability stack that we are trying to build as part of the National Cybersecurity Research Program. So on the top end, or maybe at the front end, because it's most visible to the society, is this consortium, because it involves the companies, academia, government agencies, as well as NRF. And this consortium would be engaging with a number of satellites of excellence, including the one that was mentioned, the Satellite of Excellence in Trustworthy Software. We have a couple, so it would be engaging with them, which is again building on capabilities from earlier projects. And then finally, at the bottom of the stack is really the pure research, like some of the results that I mentioned, including in fuzzing, hardening, protocol verification, as well as data protection, including trustworthy computing as in isolated execution, enclaves, and so on. Of course, I could not share all of it. So this is the overall layering of the ecosystem. This is the fully research project, which is leading to the Satellite of Excellence, which also gives out research grants. And then at the front end is the consortium, which is more liaising with the bigger society. So with that, I would like to thank the organizers once again for kindly giving me this opportunity. Thank you.
Thank you very much. Although we plan to have discussion at the end of the two lectures, if you would like to ask now, we can take one or two questions about this topic.
Yeah. Yeah, I think this is really the thing we are working on. I think the fuzzing, maybe I should use the mic. The fuzzing technology that I presented earlier and mentioned briefly, that is much more closer to maturity. So Google Brain, the fuzzing team, they run a service called OSS Fuzz, Open Source Systems Fuzz. There are similar services. This is not the only one. There is also, I think Microsoft also has the Springfield project, and there are a few others. But the OSS Fuzz is something which is available to everybody. You can just upload your software and then get the fuzzing results and so on. So one of the things that we are working with them, but this work has not been completed, is to provide a smart fuzzing technology built on what I presented, but something a little bit smarter than that in the sense that it actually takes into account the file formats. This is quite important because the fuzzing is really on the input. It's really mutating the input. So the input format is quite important. The default fuzzer that is being used today on a daily basis for finding vulnerabilities, they do bit level mutations. And clearly that is not sufficient. So there is some traction in the research community on building smarter mutations based on grammars and all. But as you might imagine, those are not something that can be used at the scale of OSS Fuzz. So we are currently working with that particular team. In fact, they are the ones who did an outreach to us once they were aware of this work to transport. And if we are successful, because whether we are successful at that scale doesn't only depend on the research. There is also a lot of protocol in terms of when the fuzzing will be run, whether we are compliant with the processes that they have inside OSS Fuzz. So it's not enough that the technology they are interested in, but that's really not enough. There is also a process compliance part. So that's what my team, I shouldn't say I'm working on, I'm not actively working on. My team is currently working on. And if we are successful, then this should be available. Yeah. Yeah, excellent question. Yeah, this is indeed a very big challenge. So there are two ways in which we try to do. One I had hinted here. So we have different activities, and depending on the level of maturity of the company, we would try to gently point them to the various opportunities where they can probably benefit more from. And also, it is also not necessarily a question of only the maturity, because the company might be also pivoting to a slightly different space. So it might be very mature in its own space, but if it is pivoting to a slightly different space, maybe they need to participate in some of the training activities that we provide. So this is one way. The other way, which is very, very useful, which we have found very, very useful, but somehow to retain its utility, it is always kept informal, is the special interest groups. So we actually have 6 special interest groups. It's software security, IoT security, data security, cybercrime, mobile security, and one other I can't remember right now. So we have 6 groups, and depending on the interest of the company, we try to encourage them to participate in the special interest group discussions, which take place once a quarter. And in that small group setting, the companies are much more willing to open up about some of the challenges that they face. So for example, they might say that, well, even though we should be having a technical solution for the overall system being trustworthy, but for these parts, I'm really buying cyber insurance. I'm not having a fully technical solution. So we can probably try to deal with that in that kind of a small group setting. So after a while, it becomes self-running. In fact, after 1.5 years or so, I stopped attending most of the special interest group sessions myself, because it was kind of running by itself, and that's really the part that we would have wanted to see, rather than me always going in there. And yeah. It should be relevant to cybersecurity. We do have a few companies which where they are not, their main business is not cybersecurity, but they have to convince us that their business is relevant to cybersecurity. So I can give you an example. For example, we have one who is working on plantations. So I had to ask them that why are you interested in being part of the consortium? But then it turns out in the plantations they have to use drones for going through the plantation, and they're very worried about the drones being hacked and taken over. So in fact, some of these techniques that I mentioned, even though they appear very futuristic, is actually applicable to this company, because they wouldn't want the drones to be compromised. So there are many, many use cases which I would have never imagined if the consortium wasn't formed.
Thank you very much again. 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 Thank you very